Welcome again to Math Essential Vector Calculus. Today we are with the divergence theorem, and we'll discuss also Gauss Law for electricity and magnetism. The statement of the divergence or Gauss theorem is that the flux of a vector field through a closed surface is equal to the volume integral of the divergence over the region enclosed. So we have two things here: the flux itself, which is normally phi, and this normally equal to the vector which we are calculating the flux for, say f, and we need to integrate this one over the unit area, and in this case we need to make note that this is over a closed surface. The second quantity, which is the statement that if you have the divergence of your vector, you can still calculate the flux by using the triple integral or the volume integral of the enclosed. So if we equate this together, we get that double integral over a closed circle of f dot n ds is equal to triple integral of the divergence of this vector f d volume. And the important thing that we have two types of surfaces. The first one, which is a closed surface, this we can apply this theorem for, but in the left hand side here. But if you have another surface which is not a closed surface, this theorem is not valid. So let's move now to Gauss law for electricity, which states that the net flux through any hypothetical closed surface is equal to the net electric charge enclosed by this surface. So net flux phi E in this case equal to the Q. And let's clarify this one. If we have two charges here, but we are taking here our surface, closed surface, as a sphere, but is doesn't have any charge here, we have no charge. So applying this law, you will have QE equal to 0 over this surface. But if you have another surface which includes two charges here, say this is Q1 and this is Q2, this one is negative and this positive, this means that the total flux here should equal to Q1 minus Q2. Now let's find the integral and differential form of the Gauss law for electricity, which is one of the Maxwell equations. So starting from the previous slide, we conclude that phi E is equal to Q. We can calculate phi E by integrating double integral over a closed surface of the electric flux density D, and Q, if we have the volume charge density, this one here, integrate triple integral D volume. Then these two sides, two left hand side, we can equate together, which conclude that the integral form for the first Maxwell equation, double integral of d dot dn ds equal to triple integral rho v d volume. Now we move to applying the divergence theorem. So we'll take this one, apply the divergence theorem for it, means take the div of d here, nabla dot d. So we can now replace the double integral with the triple integral here. And now let's take the second or the right hand side from this equation, which is this one, and place here. This one will bring here. Then we have triple integral for some quantity equal to another triple integral of another quantity. So we can conclude that these two quantities are equal, which means that nabla dot d or div d equal to rho v, which is a differential form of the this Maxwell equation. Now another application for the divergence or Gauss theorem, which is Gauss law for magnetism, which said that the net magnetic flux through any hypothetical closed surface is always 0 because no net magnetic charge or magnetic dipole is enclosed, which is typical because we don't have actually in reality any magnetic charge. And if we apply the Gauss surface anywhere here, for example, this is actually a solenoid. So if we apply any surfaces, closed surfaces like sphere or whatever, so always we have no charge here. There is no charge. So then always Qm will equal to 0. Now we will try to find the integral and differential form of the Maxwell equation here. So starting from phi m equal to 0, then recall that just if we make double integral over a closed surface, in this case magnetic flux density, which is P, then phi m is equal to double integral of P dot n ds. Then we can just simply conclude that double integral of P dot n ds equal to 0, which is the integral form. Moving to the differential form, which can be found by applying the divergence theorem or Gauss theorem again. So we get this one here. So double integral will turn to a triple integral of the divergence of the same vector. And now we have this one, we know this will equal to 0. So we can conclude that, of course, b cannot be equal, b will have a value, but divergence of p can have a 0 value. So let's wrap up. We have discussed the divergence theorem or Gauss theorem and its applications, and we have derived the integral and differential form from form of Gauss's law in electricity and magnetism, which are two of the Maxwell equations. Next, we'll learn about the Stokes theorem and its application on Faraday's law of inductions and Ampere Maxwell law, which are the third and fourth Maxwell equations. Thank you.